At night, a warship doesn't look loud. Blackwater, a thin silhouette sliding forward. Step inside and the calm dies. Fans roar, pumps thrum, motors spin. The ship breathes through steel, and the first warning is a sound that does not match the last hour. On April 14, 1988, USS Samuel B. Roberts hit a mine, and the crew fought fire and flooding for hours to save the ship. So in the next few minutes, we're going to show you the exact repair sequence crews use when something breaks in open ocean, control first, isolation, triage, the fix, and the moment you bring the system back online and find out if you actually won. Stay with us, because the scariest part isn't the break. It's the restart. Before we begin, subscribe to the channel. If you want the real mechanics of naval life, the part that keeps ships alive between the headlines, you're in the right place. Section 1. The ocean never stops attacking the hardware. Ships break for boring reasons. Salt creeps into seams. Heat cycles harden seals. Vibration loosens fasteners one tiny turn at a time. Humidity turns connectors into corrosion. Even on a calm sea, the hull flexes and the plant runs hot, so air never pauses. Inside engineering, everything is heat management. LM2500 turbines run with exhaust temperatures around 1,000 degrees Fahrenheit. And that heat has to be carried away by lube, oil, cooling water, and ventilation. Seawater cools heat exchangers. Freshwater loops protect electronics and habitability. Electrical buses feed controllers and fans. Lose one loop, and you may lose the thing it was shielding. So when a pump changes pitch at 0-200, the real question is not the pump. What else just lost protection? Section 2. Control first, or you create the next emergency. The first move is control, not a wrench. Ships store energy everywhere: pressure, electricity, heat, rotation. Rush it and you get hurt, or you make the casualty bigger. Pressure is the cleanest example. A fire main commonly sits around 100 to 150 psi. High-pressure air banks can sit around 3,000 psi. Treat that casually, and a fitting can become shrapnel. So the crew isolates. Valves shut. Breakers open. Tags go on. Logs update. Then a second set of eyes verifies. You prove the system is dead before hands go in. Now, the downstream check. If you secure this pump, what else loses cooling? If you shut this valve, what else did you just starve? Chilled water sounds like comfort until you remember it may be cooling combat systems cabinets. Which is worse, the initial failure or the secondary casualty you create by skipping isolation. Section 3. The ship snaps into a structure. When a casualty starts, the ship changes posture, rolls lock in fast. The officer of the deck keeps the ship safe and predictable. The engineering officer of the watch protects propulsion and electrical stability. Damage control, central tracks boundaries, and watertight integrity. Repair lockers muster and send responders. Combat system stays alert. That division prevents pileups. The bridge focuses on sea room and a steady platform. Engineering focuses on keeping the plant stable, not chasing rumors. Damage control focuses on compartments, ventilation control, and flooding risk. Information moves through announcements and sound-powered phone circuits that can keep working even if sections lose normal power. In that moment, what matters more, speed or control? Section 4. Diagnose like a doctor. Once the space is safe enough to enter, you get clinical. You trust symptoms that do not lie. Sound, vibration, smell, heat. Cavitation talks different than a bad bearing. Burnt insulation smells different than hot metal. You read gauges, then cross-check because one bad sensor can steal time. You chase patterns, pressure oscillation, temperature drift. A breaker that trips, resets, then trips again. Suction pressure that drops like a clogged strainer. Amps that creep up like a motor is fighting load. Then you triage. What can be isolated? What can be rerouted? What standby equipment can take load? You start a backup pump, cross-connect a loop, secure non-essential loads by margin. If you can only hold one line while you troubleshoot, what do you protect first? Electrical power, cooling, or propulsion? Section 5. Stabilize the platform before you get fancy. The ocean will not give you a clean workshop, so you stabilize first. If the casualty is heat-related, speed may come down to cut load, because lower load means less heat to reject and more breathing room in cooling and lube oil. Electrical generation may be shifted so one unit can be secured while another carries the ship. Non-critical loads may be shed so vital buses stay healthy. Ship handling becomes part of repair safety. A course change can reduce roll. A speed adjustment can smooth the ride. That keeps hands, tools, and bodies where they should be. Franklin, in 1945, is the hard receipt for priorities. Hold boundaries. Protect vital spaces. Keep the ship from cascading into total loss. If you must keep one capability online first, what is it? Firefighting, electrical power, or propulsion. Section 6. The repair is a small team in a hot box. Now, the work starts. Seal swap, valve rebuild, coupling alignment, control circuit fault tracing, pump teardown, piping patch. You do it in tight spaces, around heat and noise, with the deck never promising to stay still. You move like the ship might lurch, because it might. Trades converge. Mechanical techs chase clearances, gaskets, bearings, alignment. Electricians chase faults through cabinets, connectors, and motor controllers. Damage control watches for leaks and boundary risk. Nobody works alone. One person has hands in the equipment, another reads the procedure out loud. Someone holds light. Someone runs for gaskets or a spare motor. Someone outside tracks tools and counts them back out because a missing wrench can become the next casualty. Could you do fine alignment work while the floor slides under you? Section 7. When water or fire enters, it turns physical. If seawater enters a space, the ship becomes a math problem. Holes, pressure, time. Damage control goes physical. Plug, patch, shore, dewater. Hold the boundary so one compartment does not become the whole ship. Dewatering is layered, portable pumps get rigged, strainers get cleared, discharge is managed so it does not backflood another space. Adductors can move water by using the fire main as the driving force, which is why fire main health matters, even when you are not fighting a fire. If normal power is lost, crews rig casualty power cables so essential pumps and lights keep working. Fire follows the same logic with different tools. Cool boundaries, attack the seat, control smoke because smoke drops crews faster than heat. USS Cole in 2000 is a modern receipt. After the blast, the crew fought flooding and stabilized the ship. HMS Sheffield in 1982 is the warning receipt. When fire gets ahead, the ship can be lost after the hit. Would you stay disciplined if alarms screamed and visibility dropped to inches? Section 8. Logistics joins the fight. Sometimes you diagnose perfectly and still cannot finish because the part is not on board. Spares exist, but no ship carries everything. That is when the repair expands into reporting, supply, and hard choices. If a casualty hits mission capability, the ship sends a casualty report so commanders know what is down and what support is needed. Maintenance history shows what failed before and what parts you already burned. Then the ocean supply chain moves. Underway replenishment can deliver parts while both ships stay underway. Connected replenishment separation can be about 180 feet. Cargo transfer loads on tensioned rigs can be around 5,700 pounds. Helicopters can move critical items without bringing ships as close. If nothing arrives in time, crews cannibalize from a non-critical system to keep a critical one alive, log the debt, and track the risk. When you steal a part to survive tonight, are you fixing the ship or moving the deadline? Section 9. Making parts forward changes the clock. Modern fleets are adding a new lever. Make some parts forward instead of waiting months. Shipboard additive manufacturing is not for everything, but it can remove the single missing component blocking restoration. A real example involved adductors used to support pumping and dewatering. Traditional procurement can stretch to about a year. In a Navy additive manufacturing pilot, replacement adductors were produced and installed on a destroyer, with reporting describing about an 80% reduction in timeline compared to the traditional route. Standards still rule. Materials and inspection matter, but distance stops being a cage when the ship can produce the part that keeps a system degraded. How different does that 200 pump sound feel when you know the missing piece might be made on board before the next watch turns over? Section 10. Restoration is where experienced crews slow down. Fixing the broken piece is only half the job. Bringing the system back is where ships get hurt again, because restoration is when hidden mistakes show themselves. Experienced crews slow down here on purpose. You line up the system. Valves are restored in sequence. Breakers close deliberately. Pressurization happens slowly. You check for leaks at low pressure before full pressure. You verify flow, not just that a motor spins. You watch temperatures and vibration as machinery wakes up. You listen for the sound you remember from a healthy machine. You watch for pressure drift that says air is trapped or a strainer is loading. Then you communicate limits. What is fully normal? What is being watched? What is still restricted? Everything is logged so the next watch does not inherit mystery. Yorktown at Midway is the historic receipt for this mindset. Controlled restoration, then back into the fight because time did not care. That is how crews keep a moving steel city alive at sea across 6 to 9 month deployments. Control, diagnosis, structure, teamwork, logistics, careful restoration. If this changed how you see ship life, subscribe for more. And tell me in the comments at 0 to 100 what would scare you most to lose first: power, steering, cooling, or communications.